All right, so we're going to start with number 3, and then we'll go on to the other ones. You got these football players running up the stadium stairs. Oh, kind of like you guys did the other day in your lab, in your little mini lab. Except they tell you that they give you the time. They're asking you about the power. Um, they don't tell you the height of the stairs here, but they do tell you how long they are. So that's kind of the hypotenuse of a right triangle. And they tell you the angle in it. So they're saying, hey, here are a couple pieces of information so you can find how high the stairs are. Since the players are going to have to do work to get up the stairs, and the work they're going to have to do is against their weight. So the force they're going to have to apply is going to be upwards, and so we care about the distance they travel upwards. So all of those things would be in my y here. So this is number 3. And in my y, I would say things like the players do work upwards. They apply a normal force opposite but equal to their weight. Just like you guys did going up the stairs during the little mini lab. The power will be the rate they do this work. And you could even say in here, I've kind of connected off of here, the distance is upwards to create the work. From that statement, I'm showing that I understand that for work to be created or work to be done, I have to have that force and the magnitude of that displacement, or what we've been calling distance, in the same direction, in the same dimension. All right. So that's what I would have put for the y. I'm showing I understand that they're doing work, that it's upwards, and it's work against their weight, and that the power is the rate that they're going to do this work. So those are kind of the important things to show. That I realize the only force doing work is the one that's opposing their weight, causing them to move upwards. So, start off a little mundanely in that I want to know what height they travel as they travel up these stairs. You know, I'm picturing these bleachers, or what do they call them? Stadium steps? Stadium stairs. Going up like this. And we can approximate that by the hypotenuse of a right triangle. And what do they tell me that hypotenuse is for me? 145 meters. And they said this angle is 30 degrees. And since I'm in a triangle, I remember my SOHCAHTOA. And I say, okay, well then sine of 30 degrees is opposite h over the hypotenuse, 145 meters. So 145 meters sine 30 degrees will equal h. And that will be the height that they eventually go through. If you remember from the video you watched the other night on moving the can of Coke, they were talking about it doesn't matter if you go up the hypotenuse or you went straight up the ladder or you even threw it up there. It's that distance, that magnitude of the displacement in the direction of the force, which would be the height here, that matters for the amount of work done. And now I'm going to look at my equation sheet. I'm ready to grab a couple equations. And I've got my one about how work is created, that the force and the magnitude of the displacement have to be in the same direction. That's that F parallel, delta D parallel. And then I also have next to that is my power equation, which is the power is the work per time, or the rate of work. So those are the two that I'm going to use. Work is force parallel, delta D parallel, and then power is delta work per time. And I could even have a delta there on the time, but we're normally dropping that. So, I'm interested in the amount of power they're going to do. So I'm going to, over the time. I would also need to use the force, their weight, so the force gravitational is mg. I think I'm told an average mass of 105 kilograms. And I'm assuming this takes place on Earth. So I know little g is 9.8 newtons per kilogram. And then I can end up, and I'm told the time was 60 seconds. So one more little substitution in here. I have mg delta d over the time. And now I know all of those values. My m is 105 kilograms. My g is on Earth, so it's 9.8 newtons per kilogram. I'm waiting. What's up? Okay. You can always turn the monitor. And my distance that's parallel to that force is my h, which is 145 meters, sine 30 degrees. And my time, I think mine, they told me, was 60 seconds. 60 seconds. And that's going to end up giving me a power in joules per second, or that's equivalent to a watt. So I'm going to, all numbers, kilograms, cancel the kilograms, giving me newtons, times meters. Meter is a joule, and a joule per second, this will end up being in watts, which I believe is what they asked me to do my units in, so watts. So a joule per second, which is a watt. This will equal same answer in watts. And if you have any questions on this one, call me over, let me look at your work, and I'll be glad to answer. All right, so number 3 is behind us, number 5 is ahead of us, and so we're going to look at number 5 now, where we're told that where we're told that we have an ice cube, and it requires this much energy or this much work. Another way to think about it, to melt the ice cube, and the oven delivers work or energy at this rate, because that's what the power is. And they want us to find the time needed to melt the ice cube. So how I would approach this in my Y, this is number 5, is that power is the rate work is done. And that's really all I'd need in my Y, because that's the main, there's only one real idea in this problem. So then I would jump to my equation sheet. down here. And power is, I can either think of it as the rate work is done or the rate energy is done. I'm going to use energy this time. So I'm going to say power is energy per time. And I'm looking for time, so I'm going to rearrange that and have that power time equals energy over power. Substitute in my values. 32,230 joules of energy. 32,230 joules. The power I'm told for mine is 119 watts, which remember is a joule per second, so this is going to end up giving me a time in seconds, and they want a time in minutes. So once I have my time in seconds, then I'm going to convert that to minutes and be all happy. If you need help converting from seconds to minutes, just give me a sign and I'll come over and remind you how many seconds there are in a minute. It might even be on our equation sheet somewhere. Alright, so let me know if you need individual help on number 5, and then when people are ready, we'll go on to number 6. So, we're going on to number 6, and there was the first question, how do I ever enter my answers? Right next to questions is a little plus or minus, so you can open that and close that. That way, if you don't want to see the directions on this anymore, you can minimize those also. So it's a minimize, maximize thing. Alright, so in this question, you are using the video here, and I included it because one of the reasons it's a QuickTime video, so those of you that were having flash problems won't have that problem on this. This is QuickTime. And you need to use the video for your data. So there's some of this that we would have a difficult time doing just because we need to, everyone's going to have independent data. You are going to have to, as you watch it, find out your data, you need to watch the hands of the clock. Remember, the big hand goes around once every hour, and the little hand once every 12 hours. So like in my 1.5 day period, I'm going to look for that little hand to go around 3 times, and that's how I'll know what point in the video to pause at so that I can get the data for my left, middle, and right cylinder. So you can't just watch it to the end. Everyone has a different time. Like I know when I opened this up previously, I had a 2-day time period. All right, so notice that's in red, so how much of a day you're watching the video over is going to be different student by student. Once you have your data, they tell you the weights, and they're asking you the total amount of work done by the force of gravity, the total power required to run the clock, and compare the power used in the clock to a 10-watt compact fluorescent light bulb. So when we're looking at the amount of work, the work is going to be done by the force of gravity. So we're interested in the displacement in that same direction, which would be a displacement down. So one thing I'd probably start off with here in my Y for number 6 is that work is done when force and distance are in the same direction. I'm actually going to, rather than use the word direction, I'm going to use dimension, or dim, because, you know, if they're in opposite directions, that's still in the same dimension. And that's what some people would say is negative work, because it's going to take energy from one thing and give it to something else. So the force doing the work is gravity here. So since gravity is down, the work is going to be down. I would also make sure in my Y I showed that I understand that power is the rate work is done. And just double check, but I think that's everything, that all the understandings we need to show for this problem. There might be things that you want to be careful of. Notice that you have 1.5 days, but they're looking for the total power. You want to include units of watts there, so don't use your time as 1.5 days. Use it as that amount of time in seconds. You do need to include your units, and if you don't remember that, oh, maybe you don't have to, since it's oh yeah, you do, because the last one says do not enter units for this answer. So up here, don't forget to put a space between your number and your units. So of course, work should be in joules and power should be in watts. So don't forget your conversions there. The relevant equations from our equation sheet would be that work is the force parallel and the distance in that direction. And remember, our force here is the force due to gravity, or the weight of the objects, which they tell us, and that the power is the amount of work per time. And so you can put in your values and work through it there. Let me know if you need personal help on this. I'll come over and give you a hand. Folks, someone just asked a good question. Notice this says the total amount of work done by the force of gravity. Well, that's going to be the combination of the work done on the left cylinder and the work done on the right cylinder and the work done on the middle cylinder. So then you need the total work, which would be all three of those works combined. So once you've found the individual works, then you're gonna add those up. So it's kind of like if I had to write it, the sum of the work is the work on the left plus the work on the right plus the work on the middle. Don't know why I have such a weird order there, and that would give me my total work done.